And welcome to the Descaladiata,
Hey everybody!
our live electronics show.
Yes, we have a live electronics to do tonight. It's not a school night because tomorrow is actually a holiday, a day of service here in Adafruit. But we're still going to show off some electronics tonight.
That's right. Adafruit's closed tomorrow, so your packages won't ship out until Tuesday.
That's right.
It's a paid holiday for the entire company. And for the companies out there that do electronics or really anything else, you may want to consider giving your employees a day off because they could go do something in their community.
Mm-hmm.
Martin Luther King Day, in particular, is a day of service. And if you didn't think about it this year, it's okay. You could do it next year. And there's also other things you can do, like we added paid days off for charity. So an employee can take off time, and we pay them, and they just have to do work with a charity, and it has to be a 501(c), anyone they want. And it's been working out really well. So that is our business tip.
That's our business
from
tip.
us to you. And we keep track of productivity, and you think productivity would go down with more paid days off. Turns out it goes up.
Yeah, and we're helping our community. But
let's do some electronics.
Electronics. Okay, so today I was working on some MEMS microphone stuff, and I thought I would do a stream about microphones and different types of microphones, and we'll even use the macro to check out what a MEMS microphone looks like underneath. But to start off with, most people tend to use an Electret mic. Looks like this, and there's a little capsule. Maybe you want to go to the overhead. I can show it in more detail because these are kind of cool. This is a you know what? 1 second. Clip. There you go. Electret mics have this capsule and a little sort of a sound guard, a wind guard. That lets audio through but doesn't let you damage the capsule. And then in the back there has to be a little microphone amplifier because the signal that comes out of here, the capsule is like on the microvolt, maybe like a millivolt level. You need to have a gain of at least 100 from what I remember. Maybe it's a couple millivolts, but you need a gain of 100-ish to really get something out of it. So you can get a little op amp or a specialty mic amplifier to get that signal out. And then I thought we'd also check out on the scope cam what this looks like. So you want to go to the scope cam? No, the scope cam.
Oh, that's a microscope cam.
Yeah, a
oscilloscope. You have so many scopes.
That's for later. So I'm going to hook up this Electret mic. Let's see, output, and then first, and then ground, and then power. So hold on. Plug this in. Okay, so that's on the blue trace, and so you can see as I'm talking, you can see the analog signal coming out, and it's not too bad. This is 100 millivolts per square, so especially if I'm close, it can be like a couple volts peak to peak because there's an amplifier again on it. So that's how you that's like the most basic way to get microphone input data. And for a lot of people, they'll use a microcontroller with an analog digital converter. Almost every microcontroller has an ADC these days, and so this makes it really easy. You just sample this whenever you want. You get 1,000 samples in a row every millisecond, and then you've got a second worth of data at 1 kilohertz, or you can sample even faster. What's up?
You're doing a show about electronics.
Yes.
Yeah.
Okay. So the reason I've been working on this is, can you go to the overheady again? So this is the circuit playground board that I've been working on, and to make it really easy to do audio projects, I put a microphone on, and the microphone is over here. And the microphone I picked is an analog MEMS mic. MEMS, it's like micro-machined electronics. They're very, very small, and like an Electret, it needs some analog circuitry. So here we've got a op amp and it's gain, the gain resistors. I think I give it a gain of also like 100 or 150 to get this audio signal from the few millivolts out to about 3 volt peak to peak. That'll go into the microcontroller. And that's actually worked out pretty well. Everybody's been very happy. The thing that I don't like about it is this microphone costs like 30 cents, which is not too bad, but it's not cheap. And then the op amp costs 10 cents, and then you've got 4 or 5 components. And every time you add a component, you're adding placement costs because you have to pick and place it. And that op amp is 10 cents, and the microphone is 10 cents, and so altogether it's like, about 45 cents worth of parts. And for the original Circuit Playground, I've been okay with that. That's not too bad. It is a lot more expensive than an Electret mic. Electrets can cost as little as 5 to 10 cents. They're like dirt cheap. MEMS mics are much more expensive, but you can reflow them, whereas you can't reflow Electret mics, which kind of sucks. And also they almost are always through a hole. You can get surface mount ones, but you still have to hand solder them. They can't go through the reflow oven. And I wanted to make this easy to manufacture so everything's pick and placed. Okay, so fast forward to now the, can you go to the face cam?
Face cam?
Well, me cam.
Okay. We should come up with camera names.
Yeah, what do you want to call this camera? Main cam?
Brian.
Brine?
Yeah, like
like a salt bath?
Brine.
Okay.
Like sea monkey.
Oh, like sea monkeys. Okay.
This is sea monkey cam.
Okay, sea monkey cam. Okay, so back to the sea monkey cam. So for this Circuit Playground, which is the new version I'm working on, I have a new processor, the SAMD processor, which is much more powerful than the original AVR processor. And one of the benefits of that is it has built-in non-analog microphone inputs. So instead of having an analog input, for the beta, I basically cloned the circuit, connected to an ADC, and again, it works great. But, wow, wouldn't it be awesome if I could get rid of a whole bunch of that circuitry and save myself a ton of space and maybe even some money? So, marry our purchaser, who is awesome, I basically said, hey, can you contact every company that has an I2S or PDM MEMS mic, a digital MEMS mic, and tell them, look, we'll buy thousands from you if you give it to us at the same price as this analog microphone, like 35 cents. And a couple actually came back and said, yeah, sure, if you're going to buy at least 50,000 a year, which is kind of like what I think we'll end up buying, they said they'd give it to me for 40 cents. So for 40 cents, I can get rid of 6 of these components and maybe have good or better quality. So the next step is I'm going to move from an analog microphone, which is like you saw in the scope, it has an analog signal, to a digital microphone. And that's when I researched all about PDM versus I2S microphones and analog microphones, and I learned a lot. So the next question is, Phil, do you think I should do a whiteboard demonstration thingy, or do you want to go straight to the cool MEMS?
Well, we're going to be doing a lot of experiments tonight, so let's go right to the microscope.
Let's go to the microscope cam, or macro cam.
Yeah.
So this is a MEMS mic on the macro cam, and this is so cool. So this is 3 millimeters by 2 millimeters, but really big. So you can see on the right is the 2 diaphragms. I don't know exactly why they have 2, but those are I don't actually know exactly. Maybe it's like a piezo type element. It's something where as it deforms, you get a micro voltage out or some sort of signal output. So normally you would use a piezo or something. Piezos, when they bend, they give you a voltage. I actually didn't look up what material this is, but it's some sort of diaphragm that when air pushes, it creates a signal.
So why don't you, wrong one. Why don't you come over and point to what you're talking about here?
Okay, so, oh no, see this is...
Yeah, I'll get out of the way.
Yeah, but I just bumped it.
It's okay.
Oh, God.
So point to the membrane part. I'll get out of the way here.
Okay. So, this is... Hold on. I can also kind of shift it. Dude, it is really hard to get this lined up underneath the microscope. Okay, so these are the 2 membranes here. Again, I don't know why there's 2. In the diagram in the data sheet, it shows membrane, there's just 1. And you can even kind of see some cross-hatching. It's kind of interesting. And then remember a couple days ago we did chats about wire bonding. So you can see the wire bonds. I think this wire actually was connected over here. So that's a little sad. But there was, this came off when I hot aired the hell out of this thing to take the cap off. So these are probably used to be connected. And you can see this is bonded to, that white stuff is bonding material. Anyway, so these 2 bonding wires connected to this thing. And this is a chip with a protective like a cure epoxy over it. And then, so this chip takes these 2 signal wires and it does some sort of processing here. And then you've got, this is the I2S mic. So you've got digital, ground, I2S data, left, right, select, and I don't know, reset or something. So there's 6 wires basically for this chip. So what's neat is this package is actually like a metal case with a chip here. And then it's a separate sort of like element. So this is like a, made with the CMOS process, and this is made with a MEMS process. And there you go. And you get some like nice wire bonding here too. So that's pretty cool.
Okay.
Okay. So that's what's inside these.
That's the weather report.
And that's why they're expensive, because this is a pain in the ass. Like you have to get this metal tin, and then you have to like get this like custom MEMS, and you have to bond this other thing, and then you have to epoxy it, and you have to protect it, and you have to make sure there's no air gaps. So I'm not surprised that these are 40 cents. That's not, that's not upsetting to me. But they're not as cheap as Electret mics. Okay, so then I think we'll do this. We'll get as much as we can done today. Maybe we'll talk about PDM mics more later. Okay, so.
Oh, I'm gonna go.
Let's go to Brine Cam.
Sea Monkey.
What's the name of the sea monkey from Space Ghost Coast to Coast?
Someone in the chat will probably know.
If somebody knows, please.
This is their way of participating with us.
Yeah.
Tell us what the name.
Yeah, Space Ghost Coast to Coast, and he has like a monkey, and he's like.
Grape ape?
No, it was a brine. I can't remember. Or sea monkey. I don't remember the name of it. Anyways, okay, look. So normally you want to read. So you had your Electret mic. Like this is Electret. Or, you have an analog MEMS. And, the output is an actual sine wave. You actually get an analog output. It's not very much. It's, maybe
Someone
like...
said banjo.
That's right, banjo. Banjo! Banjo! Thank you, person who said banjo.
Stuff with Kirby, thank you.
Thank you, Stuff with Kirby. Your Space Ghost Coast to
We are a
Coast.
community. We're participating together on the internet.
So this is, like, I don't know, 10 millivolts peak to peak. It's really not that much until you amplify it. But you actually get an analog output, just like you saw on oscilloscope cam. And again, this is really easy to input into your microcontroller, and you can sample it whenever you want. You want to sample it like 1 kilohertz, go to town. You want to sample it 10 kilohertz, whatever. It doesn't matter. You can sample it as high and low as you want. The Electret mic will have a frequency response, usually, like 100 to 10,000 kilohertz, but you pretty much have a lot of flexibility with what you want to do. If you want to stop reading, you stop reading. You don't have to worry about synchronization or anything. It's just pure analog. But, you have to amplify it, which is annoying. And also, there's a lot of chips, like higher end chips, that don't have analog inputs necessarily. And also, sometimes analog digital converter is a little slow. I don't think that's the main reason why people don't go with analog. I think the main reason is these are single-ended outputs, so they can get noisy. Even if you look at the oscilloscope cam, we will again later, it's a little noisy. Yeah, it's just, it's easy for it to couple in digital noise. So if you have, especially you have like that Google Home device or the Amazon Echo or Alexa, and they have like 8 microphones, you want to make sure you're getting really good clear signal, and you might even need to synchronize them. So if you go for a digital microphone. So Electret mic's great, but you know what? At some point you might need a digital mic. So there's actually 2 different kinds of digital microphones, as I've determined by buying both kinds. So the first kind we'll talk about is the I2S mic. And these are actually a little bit more expensive than the PDM mics, but they're also a little easier to understand. So the I2S mic, the way it works is you get a word, and the word is usually 32 bits. And then you get, high, low, 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 high, low, high, low. Imagine this is 32 bits worth. And the value that's encoded it's called PCM. But PCM, not that PCM is a confusing word. I think it's a very clear word, but we would normally think of it as just a digital number. So, if you want to indicate 0, you would have 0, 0, 0, 0. If you want to indicate 1, you would have 0, 0, 1. It's basically binary coded. So it's like you get, negative 2 to the 31 through 2 to the 31 values, digitally coded. And then you have a bit clock. You have a couple lines, which is one of the things that you have to trade off, which is you get a bit clock, left-right clock, and so bit clock, left-right, and then like the data out. So you have to use at least 3 data lines. The bit clock is the line that goes up and down 32 times per sample, and you have to tell the I2S controller how many times you want to go up and down. You say, I want to sample it 8 kilohertz, for example. It'll go up and down 32 times 8 kilohertz. So whatever, multiply that out very fast. It quickly gets into the multi-kilohertz, multi-megahertz level. And usually you can actually have left and right clock because you have a left and a right audio signal, so you'd actually have stereo. So it's actually twice as fast beyond that. So you get, these digital signals, but as long as your microcontroller can keep up with the signal, it's actually kind of honestly, it's basically like SPI, right? If you're familiar with SPI, you have a data line and you have a clock, and then you just have a select, which is basically the LR clock is your select line. It's high for left and low for right, or the other way around. You clock the bits in, you literally turn that into a number. If you get 0, 0, 0, 0, it's 0, 0, 0, 0, 0, 1, it's 1, 0, 0, 0, 1, 0, it's 2, your standard binary. It's, I think it's signed, I can't remember, but I'm pretty sure it's signed data. And then you convert that into a number, and then you can actually plot that number. So you would, when you see it on a scope, it just looks like SPI data, basically. It's called I2S, which is often confused with I2C. Totally different than I2C. So that's I2S. And so I2S data output, we have a couple of audio amplifiers that do I2S output. One of the nice things about it, again, you don't get as much noise because it's a purely digital right up to the output. So you get, you don't have to worry about like, oh, there's an audio output. Like for example, the Raspberry Pi. The Raspberry Pi has 3 different ways to do audio output. You can do HDMI audio output, which is again purely digital, probably PCM encoded into the HDMI chain somehow. It can also do analog at the headphone port. And the way it does that is by PWMing a signal really, really fast. It has a PWM that is connected to a DMA. It can PWM it at like a megahertz. It's so fast that it has a simple filter. It comes out, it's noisy-ish, it's staticky, but it does work. People complain about it sometimes, especially if you have a lot of digital circuitry. If you have like a Pi TFT and it's running at 80 megahertz, you have a lot of harmonics that end up kind of coming into the power supply, into that filter. So you do hear it a little bit. It's not so bad, but if you're really listening and you have good amplification, you can hear it. And then the other, of course, is the I2S output, which gives you a really clean, beautiful output because you don't get any of the digital noise from the Raspberry Pi. And hopefully, as long as your I2S converter has a good power supply rejection ratio and a clean filter for the audio amplification stage, the conversion stage, the DAC stage, you're pretty good to go. Okay, so that's I2S. And I2S is actually pretty expensive because, not pretty expensive, it's more expensive, and I'll show you why. So let's can you go to the computer? Now, and here's the data sheet for an I2S output digital microphone. So it's microphone, it's that MEMS. This is actually what we showed underneath the macro cam. So you got those 6 bonding pads, and it's a bottom port. So it actually, when you solder it, there's a hole in the bottom for it to get audio. It's meant to be flat against, the PCB is meant to be flat up against something else. So whatever, this is how they come out. So they have a little detail here. Here's this MEMS element, and then there's some filter and I2S. But when you actually go down. Okay, so this is the timing diagram. So remember, there's this clock. There's this data out. It's called WS. No, sorry, WS is the word select, left-right selection. Data output comes out, and then they tell you like Usually they tell you the clock period, but usually something give you 2 megahertz. They give you the frequency response. And then, okay. So here's where they actually kind of talk about what's going on. So there's this MEMS capacitor, I don't know, some sort of diaphragm piezo or something like element. There's an amplifier, sigma delta, and then this thing, and you're like, what is that? And then, looks like what? I don't know, a sampler, whatever. We'll find out. Okay, so the amplifier buffers the output voltage of the MEMS to provide sufficient drive. Okay, so sigma delta converter converts an analog signal. So the MEMS actually gives you an analog signal, but it converts into a serial PDM, pulse density modulated signal. And then there's a decimator, which is just like the coolest thing. And if I had a band, I would call it the decimators. And then there's a low pass filter, and then a digital converter. So this MEMS mic, the I2S mic, is an analog microphone, which then has a analog digital converter to PDM, and then a converter from PDM downsample and into I2S. So there's like a lot of stages going on. So the original mic I had was just the analog section, and I did the signal sampling and stuff, the amplification. So you do pay a little bit more. You pay a couple cents more for all this extra stuff, but these are much more popular. Okay, so after you have I2S, you're like, okay, well, what's the other option? Because actually I2S microphones are rare. I don't see them very often. The more popular ones are called PDM. So let me go to DigiKey, and I'll look up PDM mic. As you can tell, I did. And the PDM microphones, there's a lot. And they're actually kind of standard. So this is a PDM microphone. Now let's open up the data sheet. So it's almost kind of a similar idea, but when I don't know if this one maybe has this doesn't even have like a demonstration of what's going on inside, but basically it's that first half of the other circuit. It doesn't have the low pass or the decimator. So I'll explain to you what PDM is, because PDM is really interesting, because I'd heard of it before, but I never really used it. Okay, so I2S, remember it's PCM with the, whoops. So can you go to the banjo cam? Banjo! Okay, so I2S, remember digital, it's like pure digital. The number you're getting out of it is like a binary number. And that's good, but like it's again a little more complicated because you have to, encode this. There's something even simpler than this, and it's called PDM. The only thing that says I don't think the Raspberry Pi has support for PDM mics. So before I talk about PDM, let's talk about PWM, right? Because PWM is, more people know about PWM. So pulse width modulation, this is really common. Like this is one of the third or fourth things you learn when you do microcontrollers or electronics, is how to PWM an LED. Because I remember an LED, you can turn it on, you can turn it off. Now if you change the resistance, you can dim it, but it's non-linear. So if you want to basically dim or color mix LEDs, what you do is you pick some sort of time base, and then you decide if this is your time base, and then you just repeat this forever. You pick, okay, is it high for 25% of the time, 50% of the time, 75% of the time, or 100% of the time? So if you go high and then low after 25%, you'll get about quarter brightness. If you go high for 50% of the time and then low, you get half brightness, 75% brightness, up to 100%. So you just change this value, how long the signal is high for, and that will change how bright it is. That's a pretty common thing. Again, very common for people to learn how to do when they're dimming LEDs. And if you think about it, you can also use this to send an analog signal. I mean, like if you wanted to transmit. So if your microphone wanted to transmit different analog signals, it could also do PWM, but then it would just change the pulse width to match like the analog level, right? So if the analog level was really low, it would be only a short pulse, and as the pulse gets longer, you would have a higher value, and that's actually kind of a simple digital analog converter, right? So people who do like a 1-bit DAC like the Raspberry Pi, it's pretty much what they're doing. They're just pulse width modulating that output like really, really, really fast. If you do it fast enough, then you can filter it and still get up to 20 kilohertz of signal output. But if you think about this, it's actually kind of a stupid system. I mean, it's a smart system. It's very easy because you usually have an 8-bit timer. And so you have a signal from 0 to 255, and then you set the output of the PWM timer to 127 when you want 50%, or 64 or 200, and you change that number, and that timer, right, as it counts from 0 to 25, it will compare the number to like a timer counter, and then it will toggle the pin for you. But if you think about what happens when you have a 50% signal, right? So let's say I want to send a 50% signal through my PWM, kind of simple DAC system. You would go high for 128 counts, and then low for 128 counts. Up again, then this is T. And then it would reset, and then you'd go again high for 128 counts, and then low for 128 counts. So this works fine, it's cool, but it actually is just really wasteful, because when you're doing this, the frequency, the natural frequency, which is 1/T, is much lower than you can get away with. When you're doing PWM, usually the higher the frequency, the better your signal to noise ratio. Well, the less frequency noise you're going to get, because you're going to be able to filter it much better to the amount of frequency signal you want to get. So, for example, you want to do audio signals, so usually 20 to 20 kilohertz. You need your PWM frequency to be at least 200 kilohertz to get anything reasonable. But if you could do even higher, if you could do like 1 megahertz, that's better. If you can do like 3 megahertz, that's like amazing, because the higher that frequency, the easier it is going to be to filter it down. There's some limitations on, you have to have like your filter be able to handle the higher frequencies, but for the most part, the higher the frequency, the less you're going to have that noise from the high frequency come in. So if you are spending 128 cycles high and 128 cycles low and then 128 cycles high, you're wasting your cycles, because if you want to get a 50% signal, why spend all this time high and then all this time low? What you could do instead is pulse high for 1, low for 1, high for 1, low for 1. Right? And now you're like 128 times faster, because instead of being high for 128 counts, you're only high for 1 count. And so this frequency is, you're already like way ahead. So this is perfect if you have only 0, 50%, or 100%, right? Because if it's 0, you have the signal low, 50% you alternate up and down, and 100% you have it high all the time. So you're like, okay, well, this is only good if you only have one, variation. But you could say, okay, well, what if I wanted to show instead of 50% signal, I wanted to do a 25% signal? Well, you could then have it, if you could have your system dynamically change so it's high for 1 count and low for 3, and then, high for another 1, and then low for 3. Now you've got 128 divided by 4, which is, 32? Now you've got a 32% increase. No, sorry, because it already divided by 128, right? So it's 64 times. If your system is smart enough that when you tell it pulse the output at 50%, it would automatically go to that 1, high, low, immediate. And when you say I want 25%, it would go high 1, low 3, high 1, low 3. You're squeezing that frequency down, you're making your frequency much higher by shortening your period of your frequency. So this is what PDM does, which is like really neat. And I think I've seen it once in a couple, I think like Phil B used it in an LED matrix project, and I was like, oh, that's kind of interesting, and I never really thought about it again. But then these microphones, that's what they do. They have this kind of signal output. So that's what the decimator does. It basically, what you have to do when you want to transform this back into an analog signal is you take, n samples, and then you count how many high ones there are and how many low zeros there are, and then like it tells you, then you just figure out the ratio. And as long as your sample rate is larger than the max PDM period, you're good to go. You just take your running average. It works pretty well. Neat, huh?
That's cool.
It's cool. So that's what PDM does, and I get it, but you do need to have. Well, you don't need to have. You basically have to kind of have special hardware. I mean, you can do it with an AVR. You could bit bang this, but it helps a lot if you know, especially if you're. This goes very fast. This is megahertz or higher.
You have an M0.
We have an M0, and the M0 has an I2S and PDM subsystem in it, which I haven't tried the PDM one, but I can show off the I2S one, and then you can reconfigure the I2S into PDM. Anyways, so is there any questions about that?
People are just talking in chat.
Okay.
Keep going. So what do you want to show next?
Okay, so the next thing I wanted to show is I actually have, we won't get to the PDM mic, but I can show off the I2S mic.
Sure.
Because I got, basically not knowing which one would work out, I was like, well, I'll just get samples of both. I made little breakout boards for each one of them to try out both of them. I2S I was pretty confident would work out. PDM, again, is less expensive. And it uses a heck of a lot less pins. You only need the clock pin and the data in pin. And what it does for left-right, it's actually it's a little bit weird. The left-right, it basically either samples on the low of the clock or the high of the clock. So PDM can really only, well, I get it. I mean, it's okay. I'm only using a mono microphone anyways, so that doesn't matter. So I only use 2 pins. I get 1 pin less. But that's good. So it's pretty easy to implement. You can do it. You can do bit banging. You just have to have a 1 megahertz signal. So it's nice if you have a subsystem. The M0 has a DMA subsystem as well. So you can tell it, hey, go off, get me a couple hundred samples. Come back when you're done, and then you can do what you want with them. So I thought first let's go to the I2S mic. So can you go to the Elmo cam? Okay, so this is that Electret mic, and this is the MEMS mic. And so the thing about the MEMS mic is you can't see it because it's a bottom port. I have another one maybe I could show off. So this is what it looks like on the other side. And then, but on the bottom, you see that hole in the center underneath the Adafruit logo? That's the port. So the it's meant to be mounted flat against something, so that's why it's upside down. So when I finish the final design, I'll put the text on the front because I kind of forgot about oh yeah, it's going to be upside down because otherwise you can't hear anything. And then I have it hooked up to a Feather M0 using the I2S pinout, and I actually even pulled in the latest Arduino core. I'd written some I2S stuff, or like Tony DeCole had written some. I don't remember who did. It was a couple months ago. We wrote some I2S code, but there's actually a support library now in Arduino that takes the ASF core, the not core, and kind of wraps it up into a library. So we can try that out. So if you can go to the computer cam, and do you have can I have some fluid?
What?
Can I have some fluid?
To drink?
Yeah.
Oh.
I don't want to spill it. I just want to.
Oh, I didn't know. I didn't know if it was a prop or something.
Hmm.
It's just liquid to drink.
Yeah. Okay. So this is actually a variation of an example from the Arduino I2S library. You do your sample rate, we'll do 8 kilohertz, your bits per sample. This is actually kind of interesting. If you go back to the data sheet for this device, and it talks about the PDM format somewhere here. Where is it? Oh, maybe it was a different. Oh, sorry, I'm looking at the PDM mic. I mean the I2S mic. See, so confusing. Okay, so this is the output. So you need to have it be 32-bit. They want you to give it 64 bits total, which means 32 bits left, 32 bits right, which I think is correct. And synchronize, we clock frequency from 2 megahertz to 4 megahertz. our supports sampling rates from 32 kilohertz to 64 kilohertz. But actually, I found you can kind of change this around. It's not as sensitive to this frequency as it says. And the data form is I2S 24-bit 2's complement. MSB first, the data precision is 18 bits, unused bits are 0. Basically, the upshot is the MSB down to 18 bits is valid data. The next 5 bits, 24, 23, 22, 21, 6 bits are 0, and then the rest of the bits are tri-state. But because it's tri-state, it ends up floating high and it ends up being a 1. But the upshot is only the first 18 bits are valid. And so what we do here is start the I2S, and then I2S actually it has a DMA channel that it runs for you. So if you read the data very fast, it will actually come to you as fast. And you'll get chunks of it, which I'm still kind of working out. We'll actually just show what the samples look like, and we can kind of work it out, all this in detail as I debugged it. So let's see. So we can do like sample equals I2S, and then we can just serial print line sample. Just upload this. Maybe I'll put this back in. Now, I'm actually not going to use I2S in the circuit playground, but I thought it was good for me to practice playing with I2S on an M0 because I haven't tried it with a microphone. So this is the data output. So you can see every other signal is -1, and then you get like data, which actually looks like it might be valid because it's changing around a little bit, which is normal because I'm talking while it's taking signal. So that -1 is because this is a mono microphone. And so the opposite signal is going to be all like FFFFF, right? Because I'm only using like left channel. I don't know which one it is, left or right. I'm only using one channel. And so we want to skip the other half of the audio. So let's get rid of the audio half. Oh, don't forget to put the print after the return. Okay, much better. And another thing that's kind of neat is you can sort of see as I speak that the numbers are moving around. So that's kind of a good sign. But they're like really negative and they're kind of hard to see what's going on. So we're going to use the serial plotter because it's cool. So this is a serial plotter. And as you can tell, as I speak, you're going to get signal. Now the thing is about the serial plotter, it's kind of a blessing and a curse, is it will automatically change the scale. So as I'm speaking, this scale, these numbers are changing around. Which makes it a little tough to tell what the true scale is. But the first thing we want to remember is, remember only that top 18 most significant bits are valid, so we want to shift away the unused bits. And we get 32 bits normal, and that's why I've got this line here, convert to 18 bits signed, which takes the sample. Although, you know what, should it really be, you know what, I'm going to say it's unsigned. When I think about it, it should be unsigned, because otherwise you're going to get negative. I don't believe that I2S is signed data. No, it says 2's complement, so I guess it is signed. Okay, well, I'll change this back. Okay, so now we're back at the plotter, and it's a little bit better. Instead of like, like exponential 8 or whatever, we're getting high numbers, but they're not too crazy. Let's try, I'm going to do that unsigning thing I did. we're almost done. I have to wrap this up.
Mm-hmm.
A couple more minutes. Okay, back to serial plotter. Okay, so as we speak, and I speak loudly, and I'm looking at these numbers, it looks like it ranges from about negative 2,000 up to about, if we get closer, it's going to be a little louder, about maybe 12,000. So negative 2,000 to 12,000. So this is, I'm going to map the output, so convert it from those negative numbers. Now, why are they negative? I don't know exactly why it's not zero centered. I'm assuming that part of the deal with these mics is there's a DC offset. You don't know what the DC offset's going to be. So if I was going to use this, in a production environment, I'd have to actually do a bunch of sampling to figure out what the DC offset is. You do a really low pass filter, find out what the DC is, and then you can go back and adjust your samples to make them zero centered. But for now, let's just do this. So let's print this sample. And then you got the output, and then I'm going to do a cool hack where I write the output to the analog 0 pin, which is the DAC output. And I'll also print out, instead of just one signal, I'll print out both the sample, the digital sample, and the mapped output. So you've got the sample that's 18-bit signed, you map it from that long range down to, and again, it's 18 bits, but it's not using all 18 bits, so it's just watch out for that. Just because it says it's 18 bits of precision doesn't mean it's going to be full range 18 bits. It's a little less than that. And then, print the sample, and then if you do a comma, you'll get both output. Let's try that. And then we'll go back to oscilloscope cam after this. But not yet. Okay, so this is the plotter, and you can see, the range of the signals is different. Sometimes it locks up. I don't know why it does that. But you can see you get this red signal that's 0 to 1024, and then over here that high range signal. And then, one more thing I forgot. Because you're getting the DMA signal in, and it comes in all at once, it's basically buffered, you have to put a delay in. And the delay is going to be, I'm kind of figuring this out. But the delay is essentially 1 over the sample rate, which is about 125 microseconds. This stuff takes a little bit of time, so I'm basically going to say 110. And also I think the serial print takes a while too, but we'll see. We'll see how that looks. And then let me set up my, okay, hold on. Testing. Okay, so let's go to the oscilloscope cam. Yeah, so now you can see, hold on. Get that a little better contrast. Okay, now you can see the, it's very reflective. You can see both signals. So the bottom signal, the blue, is the Electret microscope, and then the yellow signal above is the analog output, which is mirroring what is coming from the DAC. So if you can kind of sort of see it, the yellow signal is a little blockier, but it is also a much greater signal. Yeah, there you go. So the only thing that I'm still working on is for a few microseconds here and there, it stops. I think the DMA buffer is filling, and then there's supposed to be a double buffer, but it might not get to it in time, so I'm still figuring that out. So this, would be fine as long as you're sampling a certain number of signals just to get an amplitude, maybe, a sound pressure level, but it wouldn't be. It's not ready yet for if you want to record audio to an SD card or something. It's getting there, but it's not quite there. But for my uses with Circuit Playground, it's fine. So you want to go back to Banjo Cam? And we'll wrap it up.
Which cam?
Banjo Cam. Okay, so that's the experiment so far. So that I2S is kind of working. I want to try it on the Raspberry Pi because the Raspberry Pi only supports I2S. And then maybe if I have time, next time we do a stream, I'll show off the PDM microscope, the microphone, because I think that would be really interesting to compare. And I want to see that signal too, that PWM that changes period dynamically, which is pretty neat. And that's all I got.
Okay.
I think that's good.
That was fantastic.
Yeah.
All right. Well, thanks everyone. This is Desk of Lady Ada, the live electronics show. That's Lady Ada. If you want to keep us doing this, you can do it by purchasing some things at adafruit.com. That's the best way to do it.
Yeah.
And you can also like and subscribe on our various channels. This is the Microscope cam, and you can see all the things that she talked about. There's the membranes over there. Beep and boop. Isn't that neat?
Oh, can you do one last thing? Can you go to the scope cam? Yeah, so I want to show this just because this is kind of neat, and because it's always cool to shoot. So the yellow signal is the left-right clock. So triggering on it is nice because it'll let you really see just the signal itself. So you see it's binary coded. It's changing the data. The high bits are tend to be always high. As I speak louder, you see more bits moving, and then the bottom bits, which are down here, you see that they're low. Remember they said they're low for a bit and then tri-state. So just get rid of this is just junk. And then on the opposite microphone, you see they're just like tri-stated. So you just toss out that signal because when the left-right clock is high, we don't care about this signal. We only care about a mono signal. But that's kind of neat. So that's I2S signal. And then if I actually, I have a third scope probe. I forgot, I totally went for the 4, let's see, which one is, let's try on pink. I don't remember which one is the signal I want. Yeah, there you go. So that's the bit clock. So you can see the bit clock on the bottom there. 32 bits per sample. Blue is signal, yellow is left-right clock. So nice oscilloscope cam. All right, cool. So we'll check out PDM next. In part 2, the thrilling conclusion.
Okay.
If banjo lives.
Yeah, we'll do that. Okay. Well, once again, thanks for watching tonight, folks. Oh,
yeah, this is not good.
And we'll be back probably maybe tomorrow night. But Wednesday night we have Ask an Engineer. We also have Show and Tell. We also have 3D Hangouts on Wednesday. And that's it for tonight.
Yeah.
Bye, everybody.
That's a good 45 minutes of engineering.
Yeah.
Whew, time for a beer.
While I clean up, here's a video of an egg machine.